So folks, Alex here. So the other day I was watching a YouTube video by Auroran, I believe, who was giving a talk on the Rust's declarative macros. I believe the talk is named "Everything You Can Do, I Can Do" worth with macros, and that's a fun name for a talk, I guess. The talk is really good, so if you haven't seen that, go watch it. I just really wanted to add my 50 cents on top of that, specifically because like I felt that like some parts of that talk felt a little bit more magical than it could have felt, right? So I'm talking specifically about the recursion in macros. And Auroran said that even though recursion is like technically supported, it kind of needs a special treatment to it, or otherwise it just won't work. And I just really wanted to dig a little bit into that and see what that supposed to mean actually, right? So let's go ahead and go ahead and implement a simple recursive declarative macro in Rust and see where it leads us. So I want something like count tokens maybe and ABC, and I really want that like value to be 3 here. Let's see how we could implement that. So for rules, like count tokens, right? If there is nothing to count, we just give 0, right? And if it's like head and tail, we will just add 1 to the count tokens of tail, right? And let's do like expand, and we'll see that, that value is in fact 3. So if I did something like cd and did expand, you will see that now it's 4. So that thing works, right? And as you can probably tell, there is no special treatment to it, right? It's just a good old recursion, nothing else. Works like a charm. So what's the deal about it? So let's maybe compare it to just a normal Rust function, like recursive Rust function, and see how it's different. So let's do something like factorial value u64. This is actually like my favorite example. I'm using factorials all the time. So this is like a very standard implementation of a factorial thingy, right? Um, the huge difference between that and the macro thing, actually like two of these, right? So first would be the evaluation strategy. So for the um, normal functions, we have something known as eager evaluation, right? So every parameter of a function needs to be fully computed down to its like normal form, what is called, right? Um, before like the kind of outer function could like kick in, right? So here, for example, on line 10, if the value is 10, then here it will be like 10 times, but times not the factorial 9, right? Not the kind of symbolic value of any kind, but the actual value of that factorial 9, the actual number, right? So it will be like 10 times the actual like big number, and that would have resolved into a kind of even bigger number, right? That's not the case for macro rules, right? So here, if the input is like ABC, the expansion will be 1 plus tokens BC. And this is kind of crucial here, is that the expansion won't be 1 plus 2. It just would not be that. It will literally be 1 plus count tokens BC. And so as you can probably tell, like there is a difference between how like factorial computes its stuff and how macro rules computes its stuff, right? And since like all that is actually just just a syntax really, there is another requirement to that, is that like any expansion of a declarative macro, even though that expansion could be just an intermediate one, somewhere maybe like deeply nested within the kind of call stack, but there is no call stack. Yeah, so even like deeply nested ones should actually yield kind of normal Rust syntax, right? So that's a requirement. So these two things, like non-eager evaluation and that need of like returning a valid Rust syntax, can actually be very, meaningful sometimes. So let's go ahead and implement another declarative macro that will actually have problems with that. So I want to do something like reverse, and let's say reverse is like that, xlat. So basically I want to implement a macro that will take this kind of reversed string of tokens, right, and reverse it back into normal Rust syntax, right, so that the compiler is happy, right? The thing is, if you kind of stick to a kind of most naive and most straightforward implementation of that, you will end up having a problem, right? So macro rules like reverse, right? If there is nothing to reverse, we'll give the nothingness back, right? But if it's like first TT and maybe like rest TT and a bunch. So let's see. What you would like to see here is this actually, right? This kind of makes sense. Like, why not? Right? For example, like you can think maybe it was given with that semicolon 0 blah blah, right? So first will be semicolon, so now semicolon is the last actually. And if you believe that everything else is being reversed by that reverse thingy, then that implementation should be valid, but it's not. Go figure, right? Let me change the parens here. I really want them to be like that. So that's not the case, right? And as I said, the reason why that's not the case is that at any step, at any like particular expansion, this, whatever this is, should actually be a valid Rust syntax. But it's not guaranteed that it's a valid Rust syntax, specifically because of the kind of not lazy evaluation strategy, but like not eager evaluation strategy, right? So hopefully you can probably tell what's wrong with that. So I already tried to explain it. I did my best. Like it's kind of hard to explain, but I hope you get it. So then Aurorans is started to talk about the kind of special like patterns around the recursion for declarative macros, right? So he says something like, well, we could have used something known as pushback, like accumulator buffer, in order to do the recursion. And that part kind of sounds a little bit magical if you like don't necessarily know how to like work with that stuff, right? And I just really wanted to kind of make sure that you guys understand that that pattern is not really like anything new to like declarative macros or to Rust or anything like that. It's a very, very old invention that was used for function optimization, like regular function optimization for like millennia basically. So let's go ahead and apply that kind of rule, or maybe like invent that rule or derive that rule from our regular functions, right? So instead of like writing factorial like that, I could have written it like that. So factorial, right? So value U64. But then it's like an accumulator U64 with that. And let me just comment that out. So let's analyze what's different about that implementation in comparison to that implementation, right? So that implementation takes two arguments instead of one. So it takes a value and some kind of accumulator, some kind of state that each recursive call is actually like directly passing from one invocation to another. When we reach the when we reach the base case, we actually return that accumulator. We don't really return a constant value anymore. We return the value of that accumulator, whatever this is. And we kind of pre-compute parts of that function, like non-recursive parts of that function, into that accumulator, right? So instead of doing multiplication here, we are doing it here, right? It might be a little bit weird, but what that thing actually gives you is that the recursion is now what's known as tail call recursion, right? So now like the recursive case here is basically like the last case within that function's frame, right? And basically that would enable the compiler, maybe like Haskell compiler or a Camel compiler, I don't believe Rust-C actually does it, to like eliminate the recursion altogether here, right? It will just rewrite that code into a non-recursive like for loop basically. So this is a very powerful kind of compiler technique, but we can actually utilize that compiler technique for our purposes here, right? How is that? Well, and like, how is this even useful? This is useful because if the if the recursion is actually a tail call recursion, then we are kind of guaranteed that the kind of recursive case will be a valid Rust syntax no matter what, right? Because all you do, you basically just compute this, you basically just expand this macro, whatever this is, right? Which is totally fine. So let's go ahead and try rewriting our, reverse implementation, this, into that kind of style. But as you can see, like that style actually requires some kind of, external state, right? So let's try to come up with that state here. So I want to say something like that. If we are given with like, like general tokens, right? Something like TT, like here. I want to rewrite it in a different way a little bit. So let's say like this and this. So I want to turn that from a kind of function of like one argument into a function of two arguments, right? So I want to explicitly list all those tokens here. And I really want to have that other kind of variable or other, token basically that would represent the progress so far, right? And let's see. So let's see what Copilot has to say about it. So la la la. This is super weird. This is super weird. Okay, so basically what Copilot generated is this. If there is nothing to reverse anymore, and every single token was actually put within that accumulator thingy, then we will just list whatever is written within that accumulator, right? And just halt basically. And in a recursive case, where we actually still have something to do, right? We actually like pattern match on that. And we will like call ourselves in such a way that we will, you know, like split that, let's call it like, or head maybe, right? And head is that basically, and like tail. We will split that tail, we will split that head from a tail and append that, it should be head. And that should be tail. Yeah, we basically like append that head here, and we will compute ourselves recursively on the tail. So that's like that kind of pattern is something that maybe like functional programmers are very aware of, but hopefully, you know, that makes sense for you as well, right? And the huge difference between that and our like previous implementation is that recursion here is always a tail recursion, right? Basically, we are guaranteed that we will be having a valid trust syntax each iteration, right? So expands. Let's see. So that thing actually expands into let x equal to 0, right? That's good. So that's basically it. So that's basically like the whole purpose of that video. I just really wanted to make sure that like everyone kind of understand that that special pattern with pushback, buffer, and whatnot is not really a like anything special at all. This is a very, very well-known kind of optimization within the kind of general like computation, right? For example, for that factorial function. So this is very well known, and you should not be afraid of it. And this is actually your friend. So I hope that was useful, and I guess I'll see you on the next one. See you, folks.